What you got there, Mr. Bergman?
Wow, Pop-Tarts. Totally unhealthy food for the triathlete. I know. Yeah.
I like Pop-Tarts.
Do you? Yeah.
You gonna share your Pop-Tarts?
I have food in my mouth. What are you talking about?
Are you gonna share your Pop-Tarts?
No.
Why not?
You see, it's like it's limiting. It's limiting you from excessive caloric intake.
But I like Pop-Tarts.
Well, but it'll make you fat. You don't exercise enough. So
Yeah, but
it's limiting you from your calories.
But they're chocolate.
I know. That's my favorite.
Really good.
It's kind of like my weakness. So, yeah. Well, I'm going to limit him from his caloric intake. So.
Yeah, somehow I think this is supposed to segue into our what we're teaching today, isn't it?
What are you teaching?
Oh, limiting reactants.
Hey, it's on the top of our head, right up here.
See.
Limiting reactants. So Mr. Sams doesn't get the Pop-Tart. So we're talking about limiting reactants, guys. Hey, limiting reactants. Here's like the rules. Oh, no, not rules. That's next.
This is what they are.
This is what they are. Hey, limiting reactant is a chemical that is used up in a reaction.
Yeah. So, in most reactions, we have something added to something else.
Yeah.
And then it's the one that gets completely used up, meaning you start with it, and then there's no more left in the end.
Okay, that makes sense.
Okay, and then its cousin is the excess reactant.
Cousin, I got the cousin.
Yeah, that's the one that's left over when we're done.
Okay, got the cousin. Okay.
Yeah. Now, one other word you might see this, you may see this called as limiting reagent or excess reagent. It's the same thing. Don't get confused. We will usually refer to them as limiting reactants. However.
There you go. Okay.
Okay.
So, to solve these problems, you need to follow these rules.
Yeah.
So, hey, you need to copy these down.
Yeah, we're not going to read them to you. Copy them down. You're going to learn how we use these here in just a minute.
So, pause the video and copy them down. Okay? Hey, so to completely understand that, we're going to use a bike analogy.
Yeah, more with the bike again.
Yeah, so we're going to take a field trip to my garage. And in my garage, I'm going to, or I might be on my deck. I don't know. Well, I'm going to do it here tonight. But I'm going to help us to understand the concept of limiting and excess reagents, okay?
All right.
All right, today I want to talk about limiting reactants and bicycles. Bicycles? Well, you know I love bikes. So I've brought some of my bikes. I actually have more. I know this is sick, or actually my family does. Now let's see if we can figure out bikes. Now, how many bike frames do I have? Here I have 1, my race bike, 2, my son's bike, 3, my road bike, and 4, my wife's bike. Okay. Now, we've also got wheels. Now, as you know, the recipe to make a bike is you have 1 bike plus 2 wheels. Now, below is a bunch of wheels. So let's count our wheels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 wheels. So I have 11 wheels and 4 bikes. How many bikes can I make, or bike frames? Well, the recipe is 2 wheels plus 1 frame makes 1 bike. But I have 4 frames and I have 11 wheels. How many can I make? Well, you know what? I'm going to make the bikes and then we're going to see how many I make. Well, as you can see, I've made my bikes. I got the 1, a 2, a 3, a 4 bikes. And what have I got? I've also got some wheels left over. And I'll bet you did the math, but there are 3 wheels left over. Well, you see the bike frames, these are called the limiting reactants, the chemical or the substance that you ran out of first. I ran out of bike frames first, and then I had too many wheels. So the wheels are the excess reagent. You know what I need to do? I need to go for a bike ride. Well, here I am riding my bicycle, getting ready for the race. As you can see, the limiting reaction was the bike frame. The excess reactant was the wheels. I had 3 wheels left over, and I completely used up my bicycle frames. And I made 4 bikes, and I had some real wheels are left over, right? I used up 8 wheels. Hey, no hands! I had used up 8 wheels and had 3 wheels left over. We'll see you in class. Bye-bye, I got to work out, so watch me work out, okay? Hey, how'd that work for you, Mr.
That's
Stams?
pretty cool. You need to clean your garage.
Yeah, well, it is kind of dirty.
Kinda messy.
Yeah, well, you know how it goes. So, hey, let's do some examples with actual chemicals instead of bike parts.
Okay.
So, hey, okay, so let's say we've got here. All right, what have we got here? Hey, first thing you got to start with a balanced chemical equation.
Yes,
and all
you do.
these things, get balanced equation.
Yeah. Hey, look at that.
Hey, whoa!
There's a balanced equation right there.
You know, we were nice. We decided to give you the balanced equation the first time, so you don't have to write it out.
Yeah, we'll not always be that nice.
No, we'll be mean later. Okay, so what do you do? You write down like what you know
what you
underneath
know, right,
what
exactly.
you know. Hey, we got 20 grams of mercury, 20.0 gram, and we got 5 gram of oxygen, so 5.00. And now something important to say, guys, is that the grams, not necessarily the grams, but the amounts are both of reactants. There are no amounts of products, since it is called a limiting reactant problem. So, if you see two numbers of reactants, you are most likely dealing with a limiting reactant problem.
Yep. I would say 99 times out of 100. If you're given both, it's a limiting reactant problem.
Yes, and probably in this class it would be 100 out of
100%,
100.
that's
But
probably.
yeah, there are some exceptions, but we're not going to face that in this class. So calculate the maximum amount in grams of mercury oxide, or HGO. So I'm going to write a G question mark.
Okay.
So, you know, guys, this is really easy. We've
Yeah.
done this before.
Yeah.
We just need to do 2 of them.
Yes, you just do it twice. You do one stoichiometry line with one reactant, and you do another stoichiometry
So
line
I'm going to
with
convert
the
grams
other.
of mercury, the 20 grams, to grams of mercury oxide. And then I'm going to convert grams of oxygen to grams of mercury oxide. And then I'm going to find which answer gives me the lowest
Smallest.
answer, the
Yeah.
smallest answer. And the smallest answer wins.
Right, that's the one that tells you what your limiting reactant is and what the actual amount will be.
Now, why is that, Mr. Sams?
Because the one that gives you the larger number, you're never going to be able to make that much because the one that gives you the smallest number gets used up first.
Yeah.
Once it's all gone, there's no more stuff to react.
Right, think of the bicycle analogy that you just saw in my garage.
Once all the parts were done,
We had,
yeah, once you've used up the one that you have the least number of things of, even though you have leftovers others, you can't make any more bikes.
Exactly.
Yeah.
All right, so let's do this problem. Let's
Right.
20.0 grams of Hg over 1. So this is just a gram problem. We've done this before, right, Mr. Sims?
Yep.
So grams of Hg, 1 mole of Hg. This is easy. The molar mass, we don't even have to figure it out. We just look at the table.
Yeah, it's 200.6.
200.6. That's just the atomic mass of the atom of mercury.
Yep.
And then we'll say 2 moles of Hg to 2 moles of HGO. So you're getting lots of practice on these gram problems. I should probably say the grams of mercury cancel. Now the moles of mercury cancel.
Yep.
And then I'm going to say 1 mole of HGO is so many grams of HGO.
Yep, 216.6.
216.6. The grams of moles of HGO cancel, pardon me, and we get an answer when we take all the things on top divided by the bottom. I'm going to say like 24?
21.6.
Oh, duh. 21.6 grams of HGO. Now we have to do this again. Now, one of the kind of the pains in the butts of these problem guys is that you just have to become like the stoichiometry king.
Or queen.
Or queen, yeah, whatever. All right, so are you the queen or am I the queen?
Yes.
Yes, okay. Okay, so we got grams of oxygen to 1 mole of oxygen. I don't even need a periodic table for that one. That's 32.
32. Don't put 16. It's a diatomic molecule.
O2. And then we're going to say 1 mole of O2. That 1 comes from the balanced equation right there. And 2 moles of HGO. Nice thing we have, that's an O. It's like a 6.
Is that what that is?
Yeah, 216. This
Hey,
last
we get to
fraction
repeat it.
is going to be the same because we're converting to the same deal. So that's the one thing that kind of gets the same. Mr. Sams is furiously calculating, and I'm going to get 10, 1/3. It's going to be a smaller number, isn't it?
No, this is the bigger number.
Okay, all right. So I'm bad.
67.7.
67.7 grams of HGO. So that means, now let's look at these numbers. If I start with 20 grams of Hg, I can produce 21 grams of HGO. If I start with 5 grams of O2, I can produce 67. How much can I produce?
The smallest one.
Only the smallest one. That's
Okay.
this number right
So
here.
that makes the 20 grams of Hg our limiting reactant.
Very important to understand that. That makes Hg, yes, the limiting reactant, the one that you're going to run out of. Now it's not the HGO that's the limiting, that's the product.
Right. Now let me ask you this, Mr. Berkman. How can I start with 20 grams of mercury and 5 grams of oxygen, but the one I have more grams of that gets used up first. That doesn't make sense to me.
Well, it actually comes down to the molar mass here of the mercury. It weighs 200, where this weighs 32. So that means I actually have less number of moles of magnesium than oxygen.
Now, does the mole ratio takes
exactly
take that into account too?
Plus, I use up twice as much of the mercury in the recipe as I do of the oxygen. So we kind of have two things going against us: less moles, and the fact that you need twice as much moles of mercury.
Right. So don't be fooled by the smaller number of grams of oxygen. That grams do not determine the limiting reactant. You must go through and do the math first to figure out which one's limiting.
Okay. I think we should do the problem.
Okay.
All right. Okay, so here's example 2. Hey, balanced equation. We're being nice to you.
We are. We're getting soft.
We're not going to be soft on the next example, but we will this time. Hey, determine the limiting reactant and the amount of aluminum iodide produced in the reaction when 1.2 grams of aluminum and da-da-da. All right, you can read it.
Hey, look, there's two masses of two different substances.
Hey,
does that mean it's a limiting reactant problem?
I think so. So I have 1.2 grams of Al, so I'm going to write 1.2 grams here. I have 2.4 grams of iodine. How many grams of aluminum are left over?
Oh, and it also says determine the limiting reagent and the amount of AlI3 produced.
Oh, so let's write G question mark. So we have a third problem.
Yeah, we've got some extra work to do.
All right, so let's do the first part first. Okay. All right. So, all right, I'm going to try and write small here because this is going to take a lot of space. 1.2 grams of Al over 1. So again, I'm going to convert grams of Al to grams of AlI3, and then grams of I2 to grams of AlI3, lowest one wins.
Okay.
All right, so this will be grams of Al to 1 mole of Al. Looking at the periodic table, it's like 27.
27. Yes.
Is it 27.0?
It is 26.9 something. 27.0 is close.
27 works for me. Okay. And then I'm going to say, what am I going to say?
You need to go from moles of aluminum
of Al
to moles
of AlI3. That's a 2 to 2 ratio.
It is.
And then I'm going to go from moles of AlI3, that's a 1, to grams of AlI3. Now the molar mass of that would be what?
408. Bet you didn't know that one off the top of your head this time, did you?
That one, Mr. Sams, I did not know.
Yeah.
So now when you do the math, Mr. Sams, 1.2 divided by 27 times 2 divided by 2 times 408 is what?
18.1.
18.1
grams of aluminum iodide. No naked numbers, no partially clad numbers. We want full Victorian.
You want to close on?
Full Victorian garb on those numbers.
There you go. All right, next
Head
one.
to toe, neck to ankle.
2.4 grams of iodine. Iodine, that's the British oxide.
Iodine. Well, it's chlorine, fluorine, bromine.
And iodine.
And iodine. It makes sense.
Iodine, yeah. Okay. Iodine. Are we eating? Grams of I2
I wish
to
I was
1 mole.
I wish I had a Pop-Tart over there.
Yeah. All right.
Better not get up again or that's going to disappear.
How many grams of iodine are
there? It'd be 127 times 2,
254.
so 254.
I knew that actually in my head.
Man, how did you know that?
I'm so smart. Okay,
Amazing.
So the grams of iodine cancel, or iodine, and then I'm going to say moles of iodine, and that's 3
Yes.
to 2 moles of AlI3. Okay. And now I'm going to go, this is the same fraction.
Hey,
that
it's already there. 408. I don't have to do it again.
grams of AlI3 divided by 1 mole. I know we're going fast, guys. We're very good at this. You might need to pause the video. Okay. Now,
Plug and chug.
What'd you get, Mr. Sams? I think this is going to be our very small
2.57.
Oh, 2.57 grams of AlI3. So 2.57 is a smaller number than 18.1.
It is.
So therefore, the winner.
That is the amount of product we will produce.
So
the limiting reagent or reactant is the 2.54 or 2.4 grams of I2, the iodine.
So the iodine is your limiting reactant or your LR, and your excess reactant is the aluminum. Okay.
All right. Now there's
we
one
still have
extra
one
step.
more problem.
How many grams of aluminum are left over?
So we had 1.2 grams of aluminum. We used some of them up. It's like we used up some of the wheels in the bike. Okay.
But we need to figure out how much we used up and how much is then left over.
So what we're going to do is we have to do, one more stoichiometric thing. We're going to convert grams of aluminum, or of iodine, to grams of aluminum. And we will get a number less than 1.2.
Yes.
Then what we will do is we will subtract 1.2 minus that value.
Yep. Let's do it.
So we're going to start with 2.4 grams of I2. I'm going to new screen here. 2.4 grams of I2 over 1. And then there are 254 grams of I2 in 1 mole of I2. Then we're going to say moles of I2 to moles of AL.
2 moles of AL, 3 moles I2.
This was a 2 from the balance equation, and this is a 3. And then we're going to say 27 grams of AL to 1 mole of AL. Just a gram problem. We've done a bunch of these. What do you get, Mr. Sanders?
Well, I get 0.17.
So 0.17 grams of AL. Now, what does that mean?
That's how many grams of aluminum it would take to react with the 2.4 grams of iodine.
So how many grams do we have? 1.7.
We started with 1.7.
2.
No, 1.2. You're right.
So we
1.20 actually.
We started with 1.20 grams of AL, but we only used up, that's what we started with. We used up the 0.17 of that. So what we'll do is we'll subtract 0.17 grams of AL, and that, of course, is 1.03 grams of AL. So
that's how much is left over, did not react.
So most of the aluminum still remains. We used up only a scant amount. All right, go back to the bicycle analogy. I had extra wheels. I'll say the question's kind of like how many wheels are left over.
Yeah.
Got the picture? Mm-hmm. Okay. To example number 3.
Okay.
All right. Hey, I didn't give you a balanced equation, Mr. Sams. Can you hear me?
Yeah, that's fine.
He's a wacky guy. Okay, so 90 grams of FeCl3 reacts with 9.2 liters of H2S at STP. Well, we got to write a balanced equation.
Yeah, I think we should.
All right, so we'll say FeCl3 plus H2S. That's the two chemicals, and it's going to form...
HCl is one of the products.
Oh, HCl, good. I could do that.
So the H goes to the Cl. Does that mean the Fe goes to the S?
Yeah. Oh, right. But wait a second. We have to, put it together.
Yeah.
Well, FeCl3.
Yeah.
So that means the iron's charge is plus
3.
Because, okay. And he's going to get together with S. And S on the periodic table is in column 16. So his charge is minus dos.
Yep.
So that'll be a weird one. Fe2S3.
There you go.
Now that's not balanced
Not even close.
remotely.
Nope.
So how do I put a 2? I'm going to say this is my most complex one. Put a 1 there, right? Definitely. How we did that before.
Okay.
And that's going to make this a 2, and that gives me 6 chlorines. So I'll put a 6 here. That gives me 6 hydrogens. So if I put a 3 here, hey, that's it. Ding. 2, 3, 6, 1. Okay. So FeCl3, we have 90.0 grams, and we have 9.2 liters of this. It says, what is the limiting reactant? But actually, it's almost better to ask this question.
What is the mass first? Yeah.
Mass of HCl. So I'll say question mark grams. So we're going to convert liters of this to grams of this, grams of this to grams of this. Lowest one wins.
Yep. Let's go.
All right, we'll do some stoichiometry. Stoichiometry. Say stoichiometry.
Huh?
Stoichiometry.
I can't hear it.
Okay. 90.0 grams
Okay.
of FeCl3.
No negative numbers. Fully
over
clad.
1. And now I'm going to convert the grams of FeCl3 to the moles
I suppose I should add
of
that.
FeCl3. 56 plus 71 plus 35 is like at 162.5.
162.5.
I was about to say that. 162.5.
Okay.
So grams of FeCl3. Now we're going to do the mole-to-mole ratio, and there will be 6 moles of HCl. Probably should have done the bottom first, but oh well. 2 moles of FeCl3, and the grams of HCl would be 1 mole of HCl. I don't need to have this one. This will be 36.5 grams of HCl. All right?
Yep.
So it's a gram-to-gram problem. We've done quite a few already today.
Yes, we have.
And we get
60.6 grams.
60.6 grams of HCl.
Hey, guess what?
What?
Let's do another one.
Yeah, we just got to keep doing more.
Yep, got to
Hey,
do the
but
one
this is a
with
little different
H2S.
because this is a liter to gram problem.
liters.
So I've got 9.2 liters of H2S.
And it's at STP.
So
That's
we can
convenient.
use that 22.4 number.
22.4.
Later on, we'll learn how to deal with non-STP
Yeah.
conditions. So we'll say liters of H2S to 1 mole of H2S. And that number is 22.4. And then we're going to say 6 moles
Yeah.
of HCl is equal to 3 moles of H2S. We're getting there.
Yep.
Hey, and
Hey, we could use the last one the same again.
36.5 grams of HCl to 1 mole of HCl.
And that gives us what? A small number. 0.82 grams of HCl. So obviously, this is the limiting reactant.
Yep.
We're going to run out of H2S first.
Yep.
So now what we want to do is answer the question, I guess.
Yes.
This is actually the answer to what is the mass of the HCl.
Okay. And then what is the limiting reactant? That's the 9.2 liters of H2S, the one that produced the
is the
smallest
limiting
amount.
reactant. That makes this the excess reactant.
Okay, so what amount then of the excess is left over?
So we're
We
going to
have
convert
do
liters of this
another
to grams
stoichiometry
of
line.
this.
Yeah.
All right, let's get a blank screen because we
Okay.
need more space.
9.2.
9.2 liters of H2S over 1 times 22.4 liters of
The bottom.
H2S on the bottom to 1 mole of H2S. And then we're going to say moles of H2S to moles FeCl3. Do you remember what the ratio was?
It was 2 of the FEs and
Well, let's go
3
back
of the
and look.
others. Oh, he doesn't believe
2
me.
FEs and 3 H2Ss.
What'd I tell
So
you?
you're so amazing.
I know.
And the molar mass of FeCl3 is 162.5, wasn't it?
I believe it was.
1 mole of FeCl3, and the molar mass was 162.5 grams of FeCl3. And we get, Mr. Sam says, furiously typing on the calculator, 35.
44.5.
44.5 grams of FeCl3. Now, we happen to have 90
We
something.
had 90.
Was it 90 or 92? 90, you're right. Okay. So we're going to take 90.0 grams of FeCl3 to begin with and subtract
The amount that we actually used here.
44.5 grams. Remember, these are the wheels, right? The 90 grams is how many wheels we had, and the 44 grams is essentially how many wheels we used up. And the difference between those,
45.5.
about a half of it, isn't it? 45.5
Roughly.
grams of FeCl3 remains. So just a subtraction.
Yeah.
See, guys, it's just a matter of doing stoichiometry like 1, 2, 3, 4, 5, lots of times. And yeah, it's just kind of annoying that way, I think.
Yeah, you just got to do it.
Yeah, and so you're going to do a worksheet. We're going to do so much stoichiometry, and you're going to become so good at it. You're going to be like amazing.
And that's a good thing because second semester, you
Yeah,
gotta use it.
you get to, stoichiometry is kind of like the theme for the rest of the year. Math, math, math. Okay, so I think we don't need to do more examples, do we?
I think we're probably good.
I think we're good.
Yeah.
I think you're good. You're probably tired of us.
If you want more